because it didn't work out with the plan that we initially had. So it means that I'm alone with you today, and we are going to have a usual lecture or normal lecture. So, and as long as we are here, just a small reminder, we are speaking about business intelligence. And yeah, Andres already presented to you uh, some BI relevant stuff that has to do with the execution, so the semantic part. And now we have two parts left. And today we are going to speak about logic modeling. So basically, we are going to go through the start schema to see it once uh, in details and to try to understand why exactly it's applied and what are the benefits. And we are going to also see some other examples as well. And the next week we have another guest lecture planned, and if we will have some time left, then we are going to speak about the physical representation of the logical modeling and also about the in-memory databases. But this is for the next week. I hope you can still hear me. If you have questions, just interrupt me. So, first of all, the agenda of today, so logic modeling, then we are going to speak about the start schema or extended start schema, how SAP sees it and why it's extended one. And then we are going to speak about cost of join operation, and if we will have time, then we are going to do a little bit more, look a little bit more on the real uh, analysis, how a particular SQL query could be analyzed. Logical modeling. You on the left side, you see this um, sort of straightforward steps that one may have. First of all, you have a conceptual schema, then you have a logical scheme, and then you have a physical scheme. And the interesting part is how exactly you implement them. And you have a different conceptual schemes. You have already saw them last weeks, not last weeks, I mean during the last BI lectures. And today we are going to speak sort of about the logical scheme, and next week we are going to speak about the physical scheme. What is exactly a logical scheme? This is like more or less something more tangible than the conceptual scheme. So now going to speak how the stat schema is organized exactly and what you should take care of in order to transfer later on your ideas into physical scheme. In physical scheme, in this case, it's quite straightforward. It's basically you all must know the databases, and physical scheme is the representation of those tables inside the database. I know that it's really hard to keep them separated, but this is like the way that we are trying to keep them separated. Why? Because a logical schema you plan it independent. You're not sort of thinking that much about the database. And when you're planning the physical scheme, then you really need to, in some cases, really understand how a database works that you use. How the database works, I mean, in this particular case, we are speaking about the relation database management systems. Logic modeling. So, as I told you, logic modeling is sort of the thing is how to adapt the ideas of semantic modeling, how to map how to project the ideas of those semantic modeling to the relation database management systems. In short, how to do out of bunch of ideas that you uh, already learned, or already at least heard about, how to design sort of something more tangible, some relationships. And why? Because there are many types of that you need to store data somewhere. And the logical way to do it is to use kind of a database or database management system. And there are multiple versions of database, multiple types of databases are out there. So like, for instance, NoSQL database, time series, relation database, document base, hierarchical, and so on and so forth. But as long as the most widespread ones are relation database management systems. Why? Because they're quite robust. They can be sort of they're not easy to use, but they're really robust and they can be applied in many use cases. Again, just a small recap from the last lectures, what multidimensional modeling sort of means, what exactly means the dimensions. I just want to mention it again. So just assume in the middle you have a revenue in some currency, in this case in US dollars, and you have, when you think about this revenue in some numbers, you have only the word revenue. You don't have a context to this revenue, and you don't have a context to those numbers except of number and the currency. And speaking about the dimensions, you're speaking about providing the context, those numbers. And usually the context that you have for the revenue, it's a sort of what kind of product you are using. The time perspective, it means when it was sold, on when it was delivered, when it was shipped, and so on and so forth. And then you also have a region or the place, if you wish, for sure. So it's like basically different point of views on the same data. The crucial thing to mention: without dimensions, there is no context. Without no context, there is no understanding. There is little or no understanding about the fact that you are trying to analyze. Now it's like sort of from historical point of view, no one prohibits you or no one can stop you from using the Excel, for instance, because you see, okay, we have a table, we have some facts there, why not? The point with the Excel or spreadsheets, they are getting really messy really fast. They are overloaded with information and know-hows that are like not transferable. It's a good tool maybe to start, but if you really want to do a serious analysis for the company, for many stakeholders, and when you want to analyze many processes, spreadsheets maybe not a good tool. It's a good tool maybe as the end for the end user when you integrate the data and say, okay, here's the data, you can download the data, build a pivot table in your Excel, and if it makes you happy and make your decisions based on your analysis. But still, in this case, you also have some other kind of problems like not up-to-date information, responsibility for the Excel file, and so on and so forth. And the idea is to put it in a way that those spreadsheets in some kind of form, so it will be to eliminate problems that I just mentioned to you. So on the logical side, for analysis, you have sort of something called start schema. You have used it already, and you have seen an example in the exercises. But I want to again not explain, but on this slide mention it to you. The start schema, as the name suggests, you have a sort of something in the middle and some uh, not tables, but some entities around it. In the middle, it's usually fact tables, and around it you have a dimension tables. And the point is, when you need those modeling, you need to sort of uh, let the people who is using your schema, filling it with the data and analyzing, think of the schema as the info cube, so a physical representation. It could be hard to imagine, but as long as we proceed with the lecture, I hope you'll build an idea uh, in your head how this can have a flat structure of tables that are interconnected between each other could give you at the end a cube. Actually, you don't have a cube, you have tables with the connections, and this is what you can see or you can see as the cube that you can rotate, for instance, or drill and slice and dice and so on and so forth, and slice and dice. So, like by applying where clauses or by applying group wise in your SQL. So let's move to the start schema. And as I already mentioned, semantic modeling, you already have heard it. And there are logic modeling approaches. There are many of them. There's for sure then the physical modeling approach. So logic modeling directly started with start schema. The concept is easy to grasp, but there are also other ones like snowflake schema, galaxy, dimension modeling, extended start schema, and so on and so forth. They are basically, you can treat them as the extension or adaptation of start schema. So the idea of the start schema is you have a fact table in the middle of it. So just imagine in your head, and you have dimensions that provide a context to facts that you are gathering. And then for sure at the end you have to store it or you have to implement it somewhere. This is like a physical modeling approach. We'll stop on it. I'll speak on it. I have a couple of slides on the physical modeling, but more detailed view on the model and physical modeling we will have next week. Because today I hope we'll have enough time to speak about the cost of join operation. Join operation is a SQL operation where the tables are joined. And speaking about the join operation without touching the physical nature of database management systems, it's not always a good idea. So this is already we saw. I will just skip this slide. This was a first exercise. You have an entity relationship modeling, and you can model quite a lot with this kind of modeling approach. In this case, it's again the modeling of the SAT schema. So where you have sales that were sold, and you have like some context like a store, product, and time, and those sort of entities got attributes. So it's quite straightforward to transform this kind of entity relationship model into tables. So entities are going to be tables, and attributes are going to be columns, and actions are going to be the relationship between them. Again, start schema as the concept on the left, and on the right side you have a sort of more concrete example of the start schema. I would like to stop on this example a little bit so you'll get an idea how it works. So you have a sales. This is like where you store your sales, like sales volume. So this is, let's call it a table. So you sold something today, like 1x, 10x, and you store this information inside this table. But information about where you store, when, and what are stored in other tables. So like where to store is stored in the table. I will call it not an entity, I will call it table, stored inside the table called store. Then you have table time, and then you have a table product. And the idea is quite simple. You have all the times you need here, you have all the products you need here, and you have all places that contain where your product will be sold here. And you connect those dimensions with the fact of sales fact via the so-called IDs. So basically it means sales table contain the fact on its own, a number, and then the IDs of the tables to provide a context. This schema with a number of benefits, and I will list them later on. So we have a more structured way to speak about those benefits. Um, Again, stat schema, importance of data. Now, I hope you understood the core concept of the stat schema, at least the basic idea. I think I mentioned today, I already mentioned a couple of times, 20 times stat schema for today. But now let's focus on how to do it. Yeah. So first of all, for sure, we'll start with the data. The first, what you have to take care about is the data for sure, and the it could look like a good idea to collect the data at the level that you have the data, but it's not always a good idea. So basically, data should not be collected at the level of details required only by a particular group, subject area, etc. So it means you have a process, you have something, and you collect the data, and you you always have um, this decision to perform. What kind of data I can just throw away? What kind of data I could store inside my database? So it's not always possible to store everything. Uh, you could firstly start with the following. Okay, let me save on the data that I need for current processes or for current analysis. This is a valid approach, but it's not a correct one. Why? Because you should try to collect the data at the lowest possible level of details. Why? Because this should, according to the theory, it should allow you later on to satisfy any analytical needs, analytic requirements that are about to come that you don't know yet. Let me give you an example. We previously spoke about the facts and sales facts, and you have to integrate. For instance, you have multiple shops. They're selling something, and your task is quite simple. You need to integrate sales that are done, that are performed in each shop. What you could do potentially? You could do the following. You have shop in Oldenburg, you have shop in Bremen. You could do the following. You can say, okay, I will aggregate once a day. I will run an ETL job that will aggregate sales based on each product, and I will import it into my data warehouse. By doing this, what you are losing, what kind of information you are losing? You are losing the information of the, for instance, you're losing the information when the particular uh, sales action took place. Afternoon or at the evening or something. You have only aggregated view on the data of one day. You can also exaggerate and say, I'll do it once a week. I'm just artificial example. So it means that as the time passed by, you have no possibility to create a sort of time machine to get back and say, now I need another level of granularity on the data, not a week rather than a day or an hour. This is undesirable, and you have to think about it when you are designing the schemas. So, like basically speaking, you need a fact table. Instead of putting the sales volume of the day, you should like maybe um, collect there each transaction. The idea is that it will let you to run the analysis later on in a better way. In a better way means you could satisfy requirements that are not existing yet. Also, what is important, can have a multiple stat schemas inside your data warehouse. Why? Because a single stat schema, a single factor with the dimension tables is responsible for a single process. You can still combine the process and put it like sales and delivery. You can combine it into one table. You can design your logical model in this way, but then you'll need to have sort of you need to adapt every query that you're writing. So this knowledge have to be embedded into each query. Why? Because if you're like collecting the facts from different processes in a single table, then you should be able to differentiate between them, like sold and delivered, sold and sent and delivered. So like sort of three different processes, and you have to like differentiate within the table, and you also need to differentiate within the each query that you're running. So single responsibility principle is broken here. What else? So as you can already notice, each business process requires its own stat schema to catch the data. However, combination between different stat schemas is also possible. So you can still combine them. Why? You could need it because, for instance, you want to analyze the data, analyze the items that were sold and items that were delivered. How one could do that? It's quite simple. The idea is quite simple. You can have a different start schemas for each process, fact tables, but they can share the same dimension tables. And using those dimension tables, for instance, time or product, you can still combine them inside your analytical query. Yeah. I hope I could explain the core ideas. Now let's move to the elements. The description of those elements are really verbose, so you have a lot of information, but I hope note important information for you. I hope it will help you to prepare yourself for the finals, if you know what I mean. So let's move to the content. Fact table. It's I mentioned it really many times. So it's basically a primary table with for dimensional of a dimension modeling scheme. Facts are usually, it's important also, numeric measurements, so like values, cells, for instance. Facts could be computed or derived at the runtime. So like KPIs, key performance indicators or metrics. So this is quite important concept. As long as you have a not not all numeric numbers could be computed. So if you have an order like 1, 2, 3, 4, 5, and so on order, if you sum up the order, it make no sense. So it's simply an order. Order, I mean not the order when you order something. Order, I mean when you list something, like the first one, the second one, the third one. If you sum it up, it makes no sense. So maybe it's not despite being a number, it's not summable. Let's go like this. But saying, okay, this is number one, and we have five of it, so summing up the amount makes sense. Then it should have two or more foreign keys to connect itself or to connect the fact to a dimension tables. I already mentioned it many times, but still, you have this imaginary table with an ID, with the fact, like a sale, order, or whatever. Then it's have a foreign key that refers to the dimension table, so another table. And what is also important to notice, it's also had its fact table has its own primary key. It could be a set of foreign keys, all usually it's auto increment. So basically, it's a technical key that is advised to be used. And at the end, fact table is dedicated to express many-to-many relationship between dimensions. Dimension tables. Already mentioned, provide context to the fact. It's like they cannot live without each other. Dimension table is just nothing without fact table, and fact table is nothing without the dimension table. It usually contains the textual description of the business process. For instance, you have a dimension called time, yeah? And you have, like, for instance, inside this dimension, besides having a date, you have also textual information such as months. So, and months can be in different languages. Let's say months in French, months in German language, and so on and so forth. And you can use different fields according to the location or according to the preference of the user who is generating report based on the query that use this time dimension. This is a bit complicated, but we have an example on it, I think. We had also task on it. So just to grasp your idea why those dimensions are required and how they could be potentially used to improve the user experience, as a lot of marketing prospects are saying, improve the user experience by using different languages. It's defined via a single primary key, so for sure, as long as the fact table is using foreign key to refer to the dimension, the dimension table should have a primary key. Usually have a lot of columns, and this is also important, highly denormalized. If you would like to normalize the table, the dimension table, then you will end up, which is also to some extent fine, but you have to be aware. Just imagine that you have another table that sums up some moments of the dimension table. So you're just doing the normal denormalization of the tables, of the entities, in order not to duplicate the information. Totally fine. But you end up not with the start schema, you end up with the snowflake schema, which is also to some extent fine, but you don't want to forget that each additional table that you need to join could potentially decrease the performance of your analysis. So, like all the usual trade-off: denormalized data inside the tables, or normalized, perfectly normalized data, and a lot of processing power during the joins. So, surrogate keys. So, also important concept, but if you in your life once created a table, you face this surrogate key concept. Um, so surrogate key is basically a technical key that is not connected to operational key. So for instance, um, you have a shoe, you are selling shoe, or you're selling another product, bicycle, and this bicycle got a number, some article number or whatever. And technical key for this dimension could be a totally random number, totally random integer that is not related to it. Why it's required? You remember the slowly changing dimensions. So it could help you in this case. So if someone updated the color or whatever of the product, you can just insert new one and mark the old one as the old one and still be able to use them inside your queries. So you will have basically two products that sounds different, but they're the same, and you can spot the time when the change happened. So this is one of the possible scenarios why technical key unrelated to operational key could be beneficial. So they're also meaningless key. So basically, it's auto increment. It's important to mention why exactly why it's also not desirable to have a mm, to have a alphanumerical keys. It's not because of the length or something. It's basically quite pragmatical. If you have integers as your primary and foreign keys, the join operations inside the database are going to be much faster, because under the hood database management systems, they got really a lot of optimization that is based on the ability of counting 1, 2, 3, and so on and so forth. So for the database, it's harder to deal with the strings rather than to deal with the numbers. So I already mentioned it, that it separates the using a surrogate key separates the data warehouse from the operational changes. I already mentioned you an example. So of course it's you have a lot of benefits, but still you have some overheads. So like if your products keep changing every day, so you'll have all the old products, all entities of the old products, and maybe the mentioned table will grow in the same pace as the fact table, which is sometimes undesirable. By the way, there is also a possibility, it's not listed here, there is also a possibility if the dimension table is really small, so you don't want to have a really wide and huge dimension table. You can store some dimensions inside the fact table. This is undesirable, but still could be done. So I think it's called, just a second, I think it's called degraded dimensions. Exactly. Yeah. Then you have a dimension table attributes. Yeah, this is exactly what provides the context. So it's real values that are inside them. I won't stop on it, so because it's like the values that provide you with the context. And then you have a fact on its own. So this is like the answer to the question why we're doing all this stuff. So to collect those facts. A measurement of or an event that takes lots of value and participates in calculations. This is participates in calculations. It's crucial here. There are different type of facts existing. So additive facts can be summed across any dimension. So like if you have amount could be summed as the simple amount, like sold amount 2, 3, 5, 4, 10 thousand could be summed based on any dimension, time dimension, location, product, whatever. Then there is a semi-additive facts. So some facts that could not, that when you sum them up according to the particular dimension, they will not make any sense. For instance, here's an example: account balance. If you will sum it across the customers, so like group by customers, an account balance of each customer, it makes sense. But if you will sort of sum it up according to the dates or to the location, this kind of information will make no sense. This is exactly an example why the know-how of the analysis should come from or the usage of the analysis should be um, supported by the power users. You remember the power users of the BI? Because they know those facts and they know that despite it's possible to sum up unrelated revenues according to the dates, it will make no sense. And the end users may not know it because they will like trust your system. And then for sure there is no additive facts, so they can be not added. You can add them, but they will make no sense, like an order, like first one, second one, third one. If you sum those orders, it will make no sense. Do you have questions till now? Are you still able to hear me? That's perfect. Thanks, Marvin. So I will go on. So we are going to speak about the infocubes. What is this? Infocubes, it's something that I don't know whether SAP invented it, but they use it intensively inside their data warehouse. So basically, data view, info cube. I will not say the info cube. It's the same as the stat schema, one-to-one. But you can, at the back end of the info cube, you can treat it, or you can sort of think about it as the stat schema, like a fact table and then dimension tables around it that are having the same principles of interconnections. But you have, like in case of InfoCube, you have some, so it's like a standard solution. Standard solutions are usually limited to some extent, and here are limitations. MDM, master data management. So it does not support multiple languages. It have a reduced performance to the use of alphanumeric keys. I just mentioned it to you why. They're not undesired, but they're still used there, because if you will not notice this performance reduction if you don't have millions of entries and millions of facts. If you have like a small company that treats like they're selling, I don't know, they have 10, 20 sales per day, they won't reach 1 million of sales within the 10 or 20 years. So it's like making no sense for them to have this optimization. So it's like it's a solution, but to the limited number of cases. There is no support of the time-dependent change. So no support to time-dependent change means there is no support for slowly changing dimensions. So if something changes inside the dimensions, so it will be replaced or whatever. It could be a duplication of a dimension data, which is totally fine, but if you have a huge dimension, it could be a problem. Then they are sort of offered, and for sure, something new. They called extended stat schema. Basically, it's extended in a way it's sort of snowflake because each dimension table got its additional table, so with so-called master data. If you know the concept of the proxy, so when you have something in between that empowers the communication of the sites or like sort of acts as the entity that helps in exchanging the information, you can treat this PI extended stat schema as the implementation of the proxy. The idea is quite straightforward. Inside the real physical tables that are connected to the fact table, you will simply store only the IDs. And you will sort of have another table that is connected to this ID. Why it's needed? Because you can modify them independently, sort of. So just imagine that the top, what you have here, so this dimension table is going to managed by the system, like auto increment and so on and so forth, and you have sort of limited ability to manage the master data. So if you have full control of the database that is used for your data warehouse, it's totally no problem. But if you have a proprietary system, you need to do or integrate such workarounds, unfortunately. That's why it's like it's here. There's also sort of, as usual, exceptions. Also important concept to keep in mind. We spoke about the facts and we spoke about the context. But there is also a possibility to bring context together without having facts. And this is sort of called factless fact table. So it sounds strange, but still it's useful. For instance, look at the following example. Customer wants a stat schema of his stores which are located in different countries in different years. So basically, you don't have any kind of information. You basically want to join different dimensions in order to understand whether for instance, amount of shops in a particular location. So this is like could be handled by the factless table. So the names, if you know the concept of the fact table, then it's quite easy to grasp the concept of factless table. How to handle fact table requires one fact, creating of dummy fact, for instance one, and just putting it as the load. So it's quite straightforward. So the classical way you are doing is as we just discussed, central table with facts, and instead of real facts, you'll just put ones there if they're connected or not. Sort of workaround. Do you have any questions till now?
I don't think I understand the fact again.
You don't, but I do, as usual for sure. So just I'll try to ask you a couple of questions and let's just discuss what we just covered. Just a second. I hope I'll be able to find. Yeah, exactly. I'll just start a poll. So the question: why should data be collected at the lowest possible level? So we just discuss it. Nice. Someone answered C. To satisfy analytical requirements of existing processes, it could be a correct answer, but you don't have to forget that we are like sort of, we don't know the process for now, let's say in details. That's why we need to like uh, make an abstract that will help us in future to answer the questions that are not existed to the moment of the creation. So I'll just publish the results. So most of you got it right. It's B. So for sure if something like any states there, it should be a correct answer. So you have to like you are planning, and as long as the better you plan, the better you perform later on. It's obvious, I think. But still, this is like have to be a dream. So you try to, you can't, in reality, you can't cover all the cases you may have in the future, but you have to like avoid silly mistakes, like for instance, storing aggregated values or deleting some values after a couple of months or something. The next question that I have: can a normalization of a database scheme be a main goal of a warehouse modeling process? I didn't mention it explicitly, but think about the dimension tables. If you have slides, I uploaded them. You can open the slide on dimension tables, and there are an answer to this question. With this question, I want to just pitch an idea that the normalization of the tables is not a primary goal of logical modeling in sense of data analysis. Why? Because you have a bit different goals. If you could achieve the perfect normalization, your potential value in the future not that high. Why? Because when you normalizing the data, your database scheme is getting complicated, and complicated in means it's like harder to use. And if it's harder to use for humans, it's also harder to use for database management system or executed by the data management systems. And this harder execution will hit you back when you have a lot of data inside your data warehouse. So I know the cases. It's, by the way, a really nice job. I had to have a guy studied with me. He started to do an analysis in a bank, and he was like always free to chat. He was always ready. Why? When I asked him back then, what are you doing? He said, I can't do nothing because I started the query. It will last for 2 hours, and I have nothing to do during these 2 hours. So the answer, I will publish it. The answer B is correct. Normalization is not a main goal of the data warehouse modeling process. The main goal is analysis of the data and possibility to answer questions and address the needs of the stakeholders in future. Just a second. I have the next question. Is it a good idea to use the same stat schema to collect data of multiple business processes? So simply yes or no. I'm not asking you to write the answer, but if you can have a couple of points why your answer is correct, you can just put them in the chat. So I'm not the only one who is speaking all the time. Just try why in the public chat so I can see. Just a couple of keywords, you don't need to post sentences. Yeah, Rami, yeah, I'll just try to interpret your answer. Yeah, it's not only the customization, so it's like every query that you will write when you combine two processes within a single fact table have to be customized, which is undesirable. I'll just publish the results. Most of you got the answer correct. And I forgot to mention this customization aspect of the fact table when you have a multiple processes inside the fact table. Processes may have a different frequency, and this can be really a disaster when you're running an SQL queries on top of this data. So different frequencies means you can analyze the time. So something happens each minute, and something happens every hour or once in a week, and you put them in the one single table, and the array events are going to be simply uh, lost, that you still have to overcomplicate your queries. So next question that I have, what is false about fact table? It's a bit harder, the question. Again, what is false? First of all, facts should be numeric measurements. So, because you have to sort of, they have to be calculatable or summable, aggregatable. They have to express many-to-many relationships between dimensions. Fact tables, should they have a primary key? I think so. Why? Because you have to differentiate between the facts. I already gave you the right answer. So a couple of seconds and I will publish the results. The answer is, unfortunately, some of you guessed it wrong or select the wrong option. The answer is C, facts cannot be computed or derived at the right runtime. This is false. They can be computed. For sure, you should have already some facts existing inside the database, inside the fact table. Then you can compute based on existing facts, new facts. Example: you have you have again my classical example. It's boring, but it's easy to grasp. Sale. You sold products. You have inside fact table. You have each product that was sold, group of products that was sold from your bills, and then you can derive a new facts based on the aggregation. You can aggregate based on the week number or day of the year or whatever, vacation, weekend, not weekend. So you can derive based on this aggregation new facts.
Yes. Oh.
That's why this is C is false. So you can derive a new facts.
Yeah.
So this have to be really simple. If you want me to ask the questions faster, I can do it also. I don't know. Unfortunately I can't see you. That's why I also can't like do a karaoke for you, so where you just see the question, then the answer, then the question answer. So it's also not working. The question: what are dimension tables used for? To present data in a normalized way inside the database. So I think we have all this question. Provide context to a fact. It's not bad. Or to save a numerical measurements representation of a fact. Don't know. Couple of 10 seconds, and then I will publish the result and explain the answer. I'm publishing the results. Most of you got it correct. The B is the right answer. Why? A is the not right answer. Dimension tables are denormalized. Just give you an example. Usually, it should be enough for the database to store a date, like a timestamp. But the dimension table, in case of the database, in case of the start schema or data warehouse, it's a really wide table that contains not only the timestamp, it contains the months in different languages, the week of the day as the name, like Monday, Tuesday, the week of the day as the number, the months as the number, and so on and so forth. So that's why it's denormalized. And the C is a description of the fact table. It's not description of dimension table. So dimension tables are required to provide the context. So it's required to know you have a number 5 sales. 5 sales of what? 5 sales of when they happened, where, what exactly, and so on and so forth. So it's a context. Okay, I have a couple of questions left. What are surrogate keys? This have to be easy. Just a second. I just will read the variants. Key attribute of a fact table generated by ETL engine. Key attribute of a dimension table generated by ETL engine. Technical key. Auto increment, GUID, etc. Natural or operation key. Name, birthday, workplace. Yeah, you are doing good. The ones who answered, I'll just a small spoil. The D is not a correct answer. If you have an idea why D is not a correct answer, can you just post it shortly, a couple of phrases? Do me a favor. So D is incorrect. Can you explain why D is incorrect? By natural or operational key, such as name plus birthday plus workplace, could be not a good idea to be used as the surrogate key, as the key in general. I won't publish the results until someone writes me why the natural or operational key are not a good idea to be used for fact table. Sorry, for dimension tables. Yeah, Ale is correct. What else? Yeah, Marvin is also a smart move. It's correct. Another example why, because again, slowly changing dimensions. I experience a lot. People are making mistakes in my name. So if your name are going to use the name, and you definitely also used at least once someone mistyped your name. So if it's going to be used as a unique name to identify you, and if someone changed the name or correct the typo, it will be really a tough situation to handle inside the ETL. So you have to be aware that something like this could happen, and it will definitely happen. So Murphy law. So nice. All of you answered the correct answer. You impressed me. Oh. Okay. If you have no questions, I'll switch to another topic of today's lecture. Just a second. So we spoke about the fact tables. Now we're going to speak about something uh, also interesting. Cost of a join operation. Why join operation? We spoke about the tables, and we spoke about the relationship between those tables, like fact table and dimension tables. You have to bring them together, and the way to bring them together is to run an SQL join. So there are multiple types of joins existing. It's like auto join, end join, cross join. But now we're going to speak about the join in general, so as an SQL operation. And the idea, so you have a lot of numbers now, but numbers are artificial numbers in order to grasp the idea. Why? We spoke about the denormalization or of the data, so it's not crucial, but still you have to you have to use this idea of non-normalized data wisely. So it's not like let's stop normalizing the data. No, it's not a good approach. First of all, before we'll discuss the join, we have to understand how the database works. As long as we're speaking about the relation database management systems, we're going to see this approach or we're going to look deeper into it firstly. So this is what I promised you at the very beginning. We're going to grasp some concepts of the physical organization of the database. Why? Because at the end of the day, we have a semantic modeling, we have a logical modeling, but at the end of the day, we write the queries in some language. In our case, it's called SQL, and queries are run somewhere inside some entity, which we call Relation Database Management System, DBMS. And maybe it's a good idea to understand roughly how it's organized. So on the left side, you have sort of initial table, so like here, and you want to filter something out of this table. And to do it, you can do it as follows. When the query comes, you can scan the table, which has the name full scan, and fetch the values that you need. So it will be transparent for you. The database will do it for you, but it could be slow, and you can really forecast how slow it could be with the time as the data grow. That's why there's something called indexes, or index are used, which is part of each database. And usually it's depends on the database, but in case I think of the PostgreSQL, the a particular kind of index is created when you are using a primary key. Why? Because the idea is primary key is going to be used for joins, and if you use some optimization technique, so like say save inside the database additional information on those fields, we can improve those join operations. It's I don't have a couple of lectures to explain you how the database work, and actually it should be for you, it should be indifferent how the database work. But I'm a fan of the idea that you have to understand at least the core principles in order to say, okay, not not to say, okay, this join is better than another join, or this SQL is better than another SQL. No. When you face in your career the problem with the performance of the database, you should know the fields, or you should be able to at least put the right keywords inside the Google, inside the in the Stack Overflow to find the solution for your problem. Because it's not course on the database, but still BI or business intelligence analysis is not possible without databases. And there are many databases, but we are speaking about the relation databases. Let's get back and imagine ourselves a database, any database, relation database management system. On the bottom, you have a file system. On the top, you have your client, dbviva, pgadmin4, where you write your queries and send it somewhere. In the middle, you have this database management system. So it's basically some magic happens, and when SQL query runs, you get your data. If you guessed everything correct, I intentionally put here some dots. So like it's not a full overview because the query have to be parsed, have to be checked, analyzed, and so on and so forth. This is not relevant for us. The idea of this slide is to explain you what amount of work database needs to do to serve you a query, to serve you your results. First of all, I'll start from the bottom. There is a spatial operating systems are really good at managing hard drives, to manage the drives, the data on the disk. But their mechanisms are dedicated for any possible use cases. Like it's indifferent whether you're saving the video files or text files or whatever files, PDF files or whatever. So it has to be fast enough. but it's still bad for the database. Database have its own idea how to deal with the data on the disk. This is exactly covered by Disk Manager and Buffer Pool Manager. Next week, if you'll have time, I will explain you what Buffer Pool Manager exactly does. But basically, Buffer Pool Manager, it's a smart management of the data in the memory of the server of your computer that is related to the database. Then you have access methods. So it's basically how to access the data in a way that the database will always be correct in answering your queries, because you remember those ACID principles. So consistency, atomicity, isolation, and durability. So this is why all those steps are needed. Then you have sort of operation execution. So basically when the real operation are taking place. And then on the top here, you have something that is known to be the most complicated part of the database. This is exactly where the optimization is happening. So query planning. So it's exactly says what on which rotation of the disk, which particular part of the table should be fetched, moved, updated, deleted, and so on and so forth. And this is query planning. It's what I wanted to mention to you, so you will know. This is what, to some extent, differentiate, for instance, PostgreSQL, MySQL, and Oracle or MS SQL. So this is a query planning. It's what the sort of the smart part of the database. So you need all this information in order to understand that now we're going to they go from the top to the bottom, and there's a lot of stuff happening inside the database management systems. And why the same logical model in form of tables could have different performance in different databases? It's not only due to the hardware, it's also due to those different components of the database. So, what SQL join exactly? At least 2 blocks must be read from the disk or from the buffer pool or from whatever. So why? Because you have different tables. Logically, they're stored inside different chunks. Hopefully, you don't need to wait for the disk to be rotated, so they're in memory. No sequential reading is possible. Why? Because table and index are usually separated. Hard drive is rotating and performing limited number of 6 per second. So it's in case no sequential reading is possible. What does mean sequential reading? Just imagine that you need a table, that you need the values inside the table with the million of rows, but you have information that you need at the very beginning, at the very end of the table, and in the middle. So at least, and the table is not inside the memory. So it means you need at least 3 rotations of the disks in order to get them. So it means no sequential reading is possible. Or you need a full scan. It means you need to read all the tables. Then you have sequential reading, but too much information is flowing through the main memory and CPU, which is undesirable. But even when the boss in cache, so you don't need any reads. The join costs only 1 millisecond per row at read. It's going to be approximately 1.5 minutes for 100,000 rows, which is really, really slow. So it's like, it depends on the computer for sure. So let's move to the next. Let's say that we have a normalized data. Now we are got a bit not higher. We moved above our structure, about the database. We don't think about the database. We think only about the structure of the our schema, and we want to estimate, like calculate in our heads what kind of how potentially our join should be executed. Uh, this is the report that we have. We have a customer, we have an office ID, we have some customer name, account ID, and branch ID. So reports using those 5 tables requires a lot of joins. Why? Because if you look at this, so this office is connected to customer, this connected to this, and this connected to that. If you need to have a branch, you need to traverse all the data. So this is, but you have not that much data on the disk. The question, how to estimate the effectiveness of the data model? I already mentioned to you the problem where everything starts. It's a disk. So, and the basically idea how to estimate how fast something could be, it's to look at your input and output operations. Yeah. So that's what we're going to do during the next slide. I'll try to do it not fast, not slow, but not boring. Why? Because I won't mention all the numbers, so you can check them later on if you want. I just want to use those slides to support my arguments. Why looking at those inputs and outputs, input and output operations for the data that you're fetching could be a crucial thing in understanding the performance of a query, of an SQL query. So let's say that we have a following query. So we have select some revenue per office name and branch name. Yeah.